All right, so we are going to talk about Newton's second law today, net forces. So, forces cause motion. If I have a book, like your big physics textbook, and I drop it from about 1.5 meters, there is a downward force acting on that book. That's gravity. And since we have that downward force, the book is going to fall down. So, that force of gravity caused the motion, caused that book to fall down. There is a net downward force on the book. So the forces are unbalanced, and because the unbalanced force exists, the book will move. So that's an important concept to remember. Unbalanced forces cause motion, cause acceleration. So the normal force is a new force I'm going to introduce to you. We've talked about the gravitational force a little bit, but the normal force is something that acts against gravity. So imagine we've got a book sitting on a table. Gravity is pulling it down, and the book is at zero velocity, zero constant velocity. It's just hanging out there. So there should be a zero net force acting on the book. So why doesn't it fall through the table if there's a downward force? There must be another force pushing up on the book. This force needs to be equal to the force due to gravity for your forces to be balanced. Because remember, unbalanced forces cause acceleration, and this book isn't accelerating. It's just sitting there. So in order to have balanced forces, we need this upward force called the normal force. So the normal force is perpendicular to the surface, which is often equal and opposite to the gravitational force. So if we just have a book sitting on a table, we have the normal force, which is equal and opposite in direction to the gravitational force, which you can see here as the W for weight. So again, the formal definition for Newton's second law states that an unbalanced force or unbalanced forces result in acceleration. And stated as the formula, we see the sum of the forces, and sum of is that big E-like character, that means sum of. So the sum of the forces is equal to their mass times their acceleration. And again, this sum of, that means we're adding forces together. Okay? The acceleration is directly proportional to the sum of these forces, or your net force. So you could call this sum of the forces or the net force. Sometimes you'll see me write it as F net, or you could see sum of the forces. They mean the same thing, okay? So this acceleration that you get from your object, from the unbalanced forces, is going to be inversely proportional to the mass. Okay, so these are important relationships to remember and to think about. So we're going to do some examples here. We have a 5 kilogram block, and it's super important for you to draw pictures for forces. We have a 5 kilogram block. It is pushed to the right with a force of 10 newtons. What is the acceleration? So we're going to do more with what we call free body diagrams, but this is a free body diagram where we draw all the forces acting on the object. So we've got a force equal to 10 newtons. And I would probably call this FAP for applied force. So applied, because this thing is being pushed. So got a 10 Newton force here. We have the force due to gravity. And we have our normal force. And these two should be equal and opposite. So usually we put a little bar, 1 bar or 2 bars, to denote that those two vectors are equal, okay? Or that the magnitude of those two arrows is equal, okay? So we need to find the acceleration. We have balanced forces in the y direction. Y is balanced, so we do not need to worry about normal, and we do not need to worry about gravity. So we're just going to ignore those. What we do need to worry about, though, is this applied force. We don't have any forces in the other direction. There's nothing there. So we do have an unbalanced force here. Since there's only one force here, the sum of our forces, or F net, is just equal to our applied force, which is 10 newtons. So we can just use our F net equation. So EF is equal to MA. F equals MA, F ma. And we're looking for the acceleration. So to solve for acceleration, we get the force divided by the mass. So that's 10 divided by 5. And 10 divided by 5 is just 2. We can't leave that as a naked number, though. Remember, we have units. So our answer is 2 meters per second squared. So that would be an example of a very simple force or Newton's second law problem. Let's do another example together. We have a 650 kilogram car that accelerates at 4 meters per second squared south. What is the net force acting on the car? So again, good idea to draw pictures. Here's our car. And it's going south. It's accelerating. So A equals 4 meters per second squared. And our mass is 650 kilograms. What's the net force? So again, we have balanced forces in the Y, so our gravity, our normal force, those are balanced. So really, our net force in the X plane is going to be equal to the mass of this car times its acceleration in the X plane. So our mass is 650 kilograms. Kilograms is our SI unit. We don't use grams, we use kilograms. So 650 kilograms times 4 meters per second squared. That should get you 2,600 newtons. And again, from our previous video, we remember that meters per second squared times kilogram, or kilogram meters per second squared, is equal to newtons, which is our unit for forces. All right, I've got one more example for you. A 1,500 kilogram ice cream truck accelerates from rest to a top speed of 45 kilometers per hour in 8 seconds. What is the net force acting on the truck? Okay, so we're looking for the net force of this truck that is moving in the X plane. We're not going to worry about, again, gravity and the normal force because we already have the mass of this truck, and we're just worried about movement in the X plane. So we've got our truck, and we have a mass. The mass of the truck is equal to 1,500 kilograms, but we don't have an acceleration. We're looking for our net force, but we do not have an acceleration. But we can find it. So this car is accelerating from rest to a top speed of 45 kilometers per hour in 8 seconds. So we have everything that we need to find acceleration. So remember, acceleration is our change in velocity over time. We have time, and we have a change in velocity, but we do need to convert 45 kilometers per hour to meters per second. So if we use our super duper special little dimensional conversion trick, we've got that value of 3.5. So remember, 3.6, sorry. We have that value of 3.6, so we can divide by 3.6 to get 12.5 meters per second. All right, so now we can go ahead and calculate this out. Our change in velocity is going to be 12.5 divided by our time, which is 8 seconds. That gets us an acceleration of 1.56 meters per second squared. And now we can plug that into our net force equation. So our mass is 1500. Our acceleration is 1.56. So our final answer, and I'm going to change the color here because I don't think that's going to stand out very well. Our final answer is 2344 newtons. Again, I'm not really paying attention to sig figs here, but if I was, we have two sig figs, so I would say 2300 newtons. Okay, so finding the net force. When you have multiple forces, we treat them as vectors. You must add the forces to get your net force, or the resultant, which is your total force acting on the object. Okay? So gotta add those forces. So here's an example for you. Stan and Kyle are pushing a 75 kilogram sled along an icy lake. Stan pushes with a force of 55 newtons, and Kyle pushes with a force of 45 newtons. They're both pushing in the same direction. What is the acceleration of the sled? So we've got our little sled here, and we have Stan and Kyle pushing the sled. So if I were to draw a free body diagram, which again we'll learn about later, I would have this applied force from Stan of 55 newtons, and I would have this applied force from Kyle of 45 newtons. So I have these two forces here, and we do have our gravitational force going down and our normal force going up, but those are balanced forces, so we can ignore them for this problem. So I have two forces, they're going in the same direction. And remember, vectors that are going in the same direction and are in the same plane can be added. So my net force is going to be 55 plus 45. So my net force is 100 newtons. We're looking for the sled. So remember, net force is for the acceleration of the sled. So remember, our net force is the mass times the acceleration. Solving for acceleration, we get force divided by mass. So acceleration is equal to 100 divided by 75, which is equal to 1.3 meters per second squared. So your answer is 1.3 meters per second squared. So again, remember, when we have vectors, you need to add and subtract them in the same, if they're going in the same direction. So we didn't have to add or subtract gravity or the normal force. Okay, here's a final example, but I think you can tackle this one. The Batmobile exerts a force of 8.5 times 10 to the third newtons east. Another force acts on the Batmobile, which with 1500 newtons to the west. If a car has a mass of 1250 kilograms, what is its acceleration? So pause the video, take a moment to try to solve this. Okay, now I'm going to try this one out with you. So 850 times 10 to the third. We move our decimal over 3 times, or we multiply by 1000. That should be 8,500 newtons to the east. So we've got a force 8,500 newtons going east. We have another smaller force of 1,500 newtons west. And so drawing this picture is going to help you see the directions that things are going in. So you can see if you need to add or subtract these. Because remember, again, forces are vectors. So to find my net force, my two forces are going in opposite directions. So I'm going to need to subtract them. So my net force is going to be equal to 8,500 minus 1,500. So 8,500 minus 1,500 is 7,000. So my net force is 7,000. I'm looking for acceleration though. What is its acceleration? So remember, F equals ma. Solving for acceleration, we have F divided by M. In this case, it's 7,000 divided by 1250. And that is going to be equal to 5.6 meters per second squared. So the Batmobile should be moving at 5.6 meters per second squared. This answer isn't finished. Remember, acceleration is also a vector. And because we have these forces going in opposite directions, it would be a really good idea to say which direction the acceleration is in. Since the eastward force is the bigger of the two, it should be causing an acceleration in that direction. So we would say 5.6 meters per second squared to the east. And then that is your final answer. Okay, next video we're going to talk about Newton's third law.